Hi everyone, my name is Tao Yang, a PhD candidate at the University of Utah. Today I will present a paper. The title is Can Clicks Be Both Labels and Features? Unbiased Behavior Feature Collection and Uncertainty-Aware Learning to Rank. When we search something online, typically we are given a list of results, not a single one. So how to learn a ranking model to rank them is very important. Traditionally, when we want to learn a ranking model, we need the feature, the model, and the label. Some learning to rank methods, the learning to rank methods can be categorized the static learning to rank methods that usually learn a static model given static feature and fixed label. For online learning to rank or unbiased learning to rank, dynamically learn model given users feedback and also assume static feature. However, the ranking feature are usually updated frequently and even more frequently than the model itself. And the static feature assumption can make the learning to rank method ineffective. So when talking about learning to rank features, what are the typical learning to rank features we typically use? Here we divided into two groups. The first one is non-behavior feature. The second one is the behavior feature. Non-behavior feature contains some static feature like the query length, document length, BM25, TF-IDF stuff, or the quality feature that is recency, page rank stuff. This kind of non-behavior feature typically are user independent. They are independent to the result ranking, to the historical result ranking. However, for behavior feature like rating, clicks, purchase, and reviews, typically they are user dependent. They are usually sensitive to the result ranking. From our existing work, that adding behavior feature can reach better NDCG than we don't use the behavior feature. Here we know that behavior feature are usually much more effective than the non-behavior feature, since when you think about that, the behavior feature are usually direct feedback from users. However, behavior feature can be collected on items that have been shown to users. But if some users haven't been shown to users, what about their behavior feature? So here we introduce exploitation bias when learning to rank. That is, here we use a small example to illustrate the exploitation bias. Here we have two items, item A and item E. Item A has been in the rank system for time, for a period of time. While item E has just entered the ranking system. So A have the non-zero behavior feature, while the item E's behavior feature is missing and got a default value. When faced with item E, the learn to rank model will only train a learn to rank model. Since the behavior feature is very strong, the learn to rank model will rely on the behavior feature to do relevance prediction. And the model will, when see the item E, the model will decide to show it, since it has a very high behavior feature. And the item E will receive more clicks, and more clicks will result in higher relevance prediction. While item E just entered, it have no behavior feature, and the learn to rank model will decide not to show it, and it will never receive any clicks, and the item E will never be discovered, even though the item E and the item A have very similar non-behavior features have the same non-behavioral feature. So item E potentially can be very relevant as item A. So here, in this kind of exploitation bias, when it exists, how do we discover item E? Is what we need to do. Generally, we need exploration. We need exploration to explore and collect the behavior feature for item E. But how? Typically, we can show results randomly, but this terribly negatively impact the user's experience. And another thing is that we can be more conservative, that we add a small random number to its relevance prediction. However, this is still very ineffective. A better exploration strategy is to do uncertainty-aware exploration strategy. That is, we acknowledge that less behavior feature means generally means higher uncertainty. And we output ranking scores distribution, and we use the mean plus the deviation as the final ranking score to boost items, to boost the uncertain items. Whereas the item has a higher uncertainty, it will get a higher boosting, and it will collect more behavior features. When we collect more behavior features, its uncertainty will be reduced, and we won't exploit in the next round. And the uncertainty can be output by like Monte Carlo dropout stuff. And then finally, we carry out experiments to evaluate our method. There are 4 datasets we are going to use: MyMQ 2007, 2008, and the Microsoft Learning to Rank datasets 10K and 30K. For 2007 and 2008 datasets, there are no behavior feature in the datasets. While for 10K and 30K, there are already some behavior feature in the datasets. And in our experiment, we remove them because we don't know how they are generated. So we remove them and let the simulated clicks, simulated user behavior be added as the in our experiment being added, being simulated and added to the feature. And finally, we will, during click simulation, we will sample query from all the datasets and simulate clicks on the outputted rank lists. And just as we said, we introduced before, we will add the behaviors, user behaviors to the feature. And we also do a new item simulation. That is, we only keep 5 to 10 documents in the beginning, and let other items being introduced to the queries candidate as the queries candidate items gradually. That means, for example, for each query in 2007, there are actually 41 documents, and we only keep 5 to 10 documents for each query, and let the other 13 documents to be gradually introduced as candidates to simulate a cold start or new item problem. Finally, this is the results. The left column is the result without behavior feature. The right column is the result with behavior feature. As you can see that not always adding behavior feature not always means better performance. That is, for example, if the top K means we don't do any exploration. As you can see that adding behavior feature can even be worse than the top than we don't add the behavior feature. And we think this is due to the exploitation bias. However, our method, UCB rank, can take the advantage of user behavior feature while overcome the exploitation bias. That means the UCB rank with behavior feature can outperform all the baselines that don't consider user behavior feature. Here the takeaway is that behavior feature is strong, but we need to do uncertainty aware exploration to collect behavior feature. In this figure, the x-axis is the time when new or relevant items were introduced to the learning rank system. The y-axis is the click rate, and as you can see that for later for new relevant items that have been introduced to the rank system in a later time, still get much more clicks, which means we discovered those relevant items, especially compared to what other baselines. Finally, this work is being supported by the University School of Computing at the University of Utah and the Amazon. Thanks. Do you have any question?